Hello. This is the second lecture about the amplitude amplification quantum computing primitive, and we're going to look at how to improve this algorithm through the so-called amplitude amplification iteration. In the previous lecture, we saw that the basic amplitude amplification algorithm consists of two phases. In the first phase, we mark a quantum state by flipping the phase using the so-called flip quantum circuit. In the second phase of the algorithm, we transform the relative phase in difference of the magnitude that we can measure, and we're going to use the so-called mirror or groover iteration. So an obvious question is, can we repeat the mirror operation again to try to further improve our probability of success? So for instance, suppose that we have the B quantum register in the following state. After the first iteration of a flip and the mirror, and this is going to be the results. So what happens if we repeat a mirror groover phase? Well, what happens, we basically go back to the initial state where we have our marker value, but the magnitude of the different state is the same. So that's not actually good for us. So what we can try to do is actually to repeat the flip and the mirror groover operation. So we have, for instance, in this quantum circuit here, we have the initial flip operation, and then we apply our mirror operation. So let's put a F here, a mirror here, and then we mark again our value by using this flip operation. So at the end of this quantum circuit, we see that we flip, so we mark again our quantum state. And then we decide to add an additional mirror operation. So we have two iterations that both consist of a flip phase, a mirror phase. So this is flip, mirror, and then we have a second iteration that consists of both flip and mirror. What we see that after two iterations of a flip mirror, the probability of finding our mark value has jumped from 47%, almost at 50%, to 90%. So we saw that adding one more iteration was very beneficial. So we have higher probability of observing the flipped state, the mark state. So the flip and the mirror subroutines are a very powerful combination. Flip allows us to target the values of the quantum register and distinguish its phase from the others. So this is the so-called marking phase. And then we have the mirror phase that converts the phase difference into a magnitude difference that we can actually measure. So in these slides, we can see the plot of the amplitude amplification iteration. We have a flip, in this case here, and then we have the mirror, that is this part here. So what happens if we apply more amplitude amplification iterations? So for instance, here we have the first one, second one, third one, and fourth one. So we have a 4 amplitude amplification iteration. You see that after the first 3 iteration, the values of observing, the probability of observing the flip values is increased up to 96%, so it's very big. But then after the third iteration, the probability of observing the flip values drops to 58%. So increasing the number of iteration improved up to 4 iteration. After that, it goes down. Let's look at a circular notation of our quantum circuit depicted on these slides. So after B2, we will have a magnitude difference that is we can see here, but no phase difference. So you see that this phase is completely aligned with all the other phases. So further amplitude amplification iteration will start diminishing magnitude difference until we ended up with the original state. So by the time that we get to B4, our chances to successfully reading out the marked state are way down to 58.2%. And they will continue to drop if we apply more amplitude amplification iteration. So the question that we might have is how many iterations we need to do of the amplitude amplification. The plots that we see here show on the x-axis the number of amplitude amplification iteration, and then on the y-axis the mark value probability. What is the probability of observing the mark value after the measurement? And we can see that the probability of reading the mark value oscillates in a very predictable way. It's basically a sinusoidal behavior. We observe that after the 9th and the 15th iteration, we get a probability of finding the mark value of 99%. So there is a simple equation to determine the number of amplitude amplification iteration that we should perform to get the highest probability within the first oscillation, and is depicted here. So we have the number of amplitude amplification iteration that gives us the highest probability within the first oscillation is equal to the floor operation of pi square root of 2 to the n, where n is the number of qubits divided by 4. We can also extend the amplitude amplification to detect two flip values using exactly the same methodology. So we applied a number of amplitude amplification iteration that consists of a flip and a mirror operation. So in this case, ideally we want to end up with a QPU register configured so that we will read the two phase flip values with zero possibility of reading any others. If we do the same technique and we apply different amplitude amplification iteration, we see that although we still get a sinusoidal varying chance of success, we also note that the frequency of these sinusoidal waves has increased, right? So this wavelength is actually shorter. We can do a very similar technique like we applied before. So it's possible to show that the frequency with which our chance of success oscillate depends only on the number of flip values and obviously on the number of qubits, and we can get an analogous equation to get the number of amplitude amplification iteration that we need to apply for multiple flipped value. In this case, we also have m at the denominator, that is the number of mark items. So what is the problem of the amplitude amplification iteration that we've seen so far? Well, the major problem is the amplitude operation assume that we know which value we want to amplify, right? So we know which qubit we want to flip, and therefore we actually flip it, right? So the flipping part is hardwired, so we know which value, and when we hardwire into the quantum circuit. So the question is, if we already know which values we should amplify, why do we need to find them? Well, it turns out that in a real application, the so-called quantum search, the flip operation will actually be replaced. It will be replaced with some more complex subroutine that typically performs a quantum conditional operation, and that is performing a combination of phase flips. So the key point is that compounding more complex phase altering subroutines with the mirror still will convert phase alteration into magnitude differences. So we will go from a flip operation that we are using right now, that is hardwired, to more like a so-called oracle, that is a quantum conditional operation that will allow us to mark a certain quantum state. The amplitude amplification iteration can be used as a subroutine on many conventional algorithms, most importantly the Groover algorithm or the quantum search algorithm, and will provide a quadratic performance speedup with respect to conventional algorithm, classical algorithm. The problem that amplitude amplification can be applied to are those invoking a subroutine that repeatedly check the validity of a solution, a so-called oracle. Example of this type of problems are Boolean satisfiability and finding global and local minima. It is in the flip part that we encode the equivalent to the classical subroutine that checks the validity of a solution. And the mirror part will remain the same for all the application, the so-called mirror Groover iteration. This is the last slides of this lecture, and talk to you soon.